Hello, can you hear me? Okay, I'll start the problem solving session now. I am Sachin Sampath, a PhD student in the EC department at IISc Bangalore, and I'll be one of the TAs for this course, and I'll only be solving problems. So other stuff like logistics and all for the course, you'll have to ask in the discussion group. So if you have doubts, you can ask, but I can't guarantee that I can solve all your doubts. But mostly, if it's related to some type of assignment question, I should be able to answer. Okay, I'll start the problem solving session. So, the way it will go is I'll first show you the question and I'll give you some time to solve it yourself. And you try it out, and then later I will solve it, and you can check if you have solved it correctly or not. So I'll just give 2-3 minutes after each question for you guys to try it. And then once I'm done with my questions, you can you can ask any doubts that are related to the material that I have covered. Okay. So here is the first question. Circuit has been given, and among the options, the output Y is at logic state 0 when. So there are four options here. So when and each of the options has a different configuration for the input values. So for option A and D are high, and B and C are low. For option B and C are high, and A and D are low. For option C, all A, B, C, and D are high. For option D, all A, B, C, and D are low. So among these options, which of them will give you the output as a logic state 0? That's the question. I'll give you 2 minutes to think about it. And if you get the answer, you can type it in the chat box, and I'll be able to see if you have solved it or not. So these questions are from previous year assignments for nptel. So if you can solve these questions, you should be able to solve your current assignment questions also, because they'll be quite similar. And even the final exam questions, they will be kind of similar to the questions we solved in the problem solving session. Okay, let me solve it since nobody has given any answers in the chat. I'll solve it for you, and if you have any doubts, you can unmute yourself and ask me. Before that, don't unmute your mic. Keep your mic muted. Okay. This a similar type of circuit was given in your lecture videos. If you have seen the lecture videos, But there was only, so in the lecture the circuit had only one of these parts. So here you can see that, let's say, if you remove this part and only consider the rest of the thing to the right of that line that I have drawn, then it is similar to the circuit that was taught in the lecture video, which was the circuit for kind of some logic gate. I don't remember which one it is, but here the only difference is that this part of the circuit has been replicated and connected in parallel. So this part, you can see that there are two of those parts and they are kind of connected in parallel. So what that means is that if it had only one of these branches, this would have been like a NAND gate, I think. This would be a NAND gate, so the output Y would be CD whole bar. And if you take only the part containing this A and B, then that would also be an AND gate which would give you AB bar. And since they are in parallel, this would be something like CD bar plus AB bar. I'm not sure if you understand what exactly I'm writing, but that's what is happening here. So if you think about the situation just in terms of electronics, then let's say one of these inputs, uh, let's say A is low. If A is low, what will happen? This VB junction is on, so all the current will flow from this VCC in this path. No current will flow in this path. Since no current flows into the base of Q3 transistor will be off. Similarly, suppose one of C and D is also low. Let's say C is low. Then this base emitter junction is on. So current can flow through this path and no current will flow through this path. Therefore, this Q4 transistor is also off. When both Q3 and Q4 are off, no current will flow through R2, so there's no voltage drop across R2. That means that there's no voltage drop here across this base emitter junction, which will mean that Q6 is also off. And since Q3 and Q4 are off, that means that this VCC, there will be some drop across R1, but the remaining voltage will appear across this base emitter junction. So this transistor will be on. So this happens whenever one of these two, A or B, is on or high, and one of these two, C and D, is also high. So the only different situation which can occur is if all the inputs are high. So none of the inputs are low. Or yeah, that's the only different situation that can occur. So we'll explore that situation. Let's say all these inputs are high. A, B, C and D are all high. So then current can't flow through the base emitter junction. Here it's off. So current can't flow through here also. That's also off. That would mean that most of the current would flow through these two paths. So there's a base current flowing here, high enough base current to turn on both the transistors Q3 and Q4. So both of these will be on. When both of these will be on, they'll go into saturation and current can easily flow through this path. So there will be a voltage drop across R2. And we are assuming that that voltage drop is high enough to forward bias this BE junction at Q6. So this transistor will also be on. So when this Q6 is on, it's in saturation, so Y will be at something like 0.2 volts, and that will be considered output is low. So that's what they had asked. Why is it logic low state when all A, B, C, and E are high, which is option C. Any doubt in this solution? If you have a doubt, you can ask me now. Okay. Since no one is asking a doubt, I'll assume that you guys understood the solution. Yeah. No, no. See, there's a circuit, this branch that has this AB that can be considered like an AND gate. And then the branch that has CD, that's also an AND gate, and it's like these two are in parallel. Have you seen the lectures or read the lecture material? So in that there is a circuit, right? That right? So there they have given a circuit similar to this, except that there's only one branch with a multi-emitter transistor, right? So the operation is same except that you have two different branches. Okay, go ahead. What were you asking? Yeah. So this thing, you understood the logic of that circuit, right? So the circuit behaved like an AND gate because when both, let's say both A and B are high, in that in that case, all the current will flow through this Q3 transistor, right? So Q3 will be on, then Q6 will be on, and then since Q6 is on, the output will go to low. That was the logic, right? But it doesn't matter whether it's Q3 or Q4 or if both of them are on. In all these situations, the same thing will happen, right? So either Q3 should be turned on or Q4 should be turned on, or Q3 and Q4 both can be on. In all three situations, this current will flow here. Yeah, and then this will be on, so it will bring it to low. So that's why it's an OR of these two branch circuits, you could say. Okay. That's why the correct answer is C. All A, B, C, and D must be high. If any one of them is low, then if any one of them in each branch it should happen. So yeah, that actually there's one more situation where this can you can get an output uh, which is in logic 0 state, but it's not among the options. So here you can see among the options, uh, B and C are low in the first option, and in second option A and D are low. So one among these and one among these is low. in both A and B. And in D, all of them are low. So if at least one of the inputs in the two branches is low, then your output will be high. Suppose there was an option saying A and B are high, but C and D are low. This option would also be right. This would also give you an output which is low value, but none of the options are in this pattern. Okay, we'll go to question 2. Again, this is a circuit that was discussed in the class in detail, the lecture videos. Uh, this is also a NAND gate, I think. DTL NAND gate. And the functioning of the circuit is not that important. The question here asks us about only this resistor R3. Why do we have this R3, and what should be the value of this resistance? Should it be high or should it be low? And the answer to that was explained in class. This R3 is needed to discharge the this base emitter junction. So when it is in, let's say when the transistor is on, at that time charge will accumulate in these regions. There will be charge across the collector emitter and base emitter. So that charge, when it is when this transistor is on, this output is low, right? So it will be low, and when we want it to change it to a high state, we'll give appropriate inputs and it will transition to a high state. But for it to go to a high state, this transistor should go from saturation to an off state, right? So for this transistor to switch off, this voltage VBE here should go below 0.7 volts. But suppose since this can behave like a capacitor, there will be capacitance here. It will take some time for the B voltage to go below 0.7 volts. If you want to make it faster, you can give it a path like what is done here by connecting a resistor. So that will give it a path to discharge all that charge it accumulated. And if you should know about RC circuit where the time constant is related to the value of R and C as a product. So if R is lower, the discharge and all will be much faster. That's why you want to have R3 should be as low as possible. So it's option C. Like some of the students have, yeah, Atharva and Jitendra both have said option C, and yeah, that is right. It's used to reduce propagation delay and proper biasing of transistor. That that is here. There should be 0.7 volts for it to be forward biased, right? That will happen when 0.7 volts drops across this resistor. It just makes sure that there's no funny business going on here. So without that resistor, it will still work, but there might be problems in specific situations. And R3 should be as low as possible. Okay. Question 3. Again the same circuit, except that they have some quantitative question. So A and B both are kept at high voltage, 5 volts, and they have given values for R1, R2, R3. also, and the diode voltage drop is 0.7 volts, and the beta for this is 100, the current amplification. And what they are asking you to calculate is voltage at the collector terminal. That is why, that is the output. What will it be? It's the same circuit. It's a NAND gate, right? And the truth table for a NAND gate is what? NAND gate A, B, and output. When both inputs are low, output will be high. When A is low, B is high, output will be again high. When A is high, B is low, output will be again high. When both inputs are high, output will be low. So here they have given that both inputs are high. So the output should be a low output. For you to get a low output, what should happen? The transistor must be in saturation, so that whatever output you get is actually the voltage across this terminal. So it's less than 0.2 volts. C is the right answer. Did you get it? Actually, BC saturation, here they have assumed that it is the same as whatever was taught in the lecture, 0.2 volts, but the output will be a little lesser than 0.2 volts. So this is if you know exactly what the operation that's happening is. Otherwise, you could still take you could do network analysis. Like you could write the KVL equations and KCL equations across this path and this path and try to solve it in that way. But that's not needed here. Okay, so it's option C. Question 4. So this was also a similar problem was solved in class, except that here the VIH is 2.75 volts, which is different, and they've asked you to calculate fan out for two different noise margins, 0.1 volts and 1 volt. Okay, so when the input is a high voltage, Vin is high, then this transistor here will go into saturation and this Vout will go to 0.2 volts, which will be fed as the input to the other output transistors here, so the load transistors, and this will be low regardless of how many transistors you connect, because even if you connect more transistors, the current division will make it so that there is lower current to each of the transistors, which is fine because the input to all those transistors should be low, right? So if we get even lower current by connecting more transistors, it's fine. So when the input is high, you don't face any problem. Only when the input is low is there a difficulty. We cannot arbitrarily connect any number of transistors. So let's see, when the input is low, the output should be high, right? And you saw in class that Vout should be at least the same as VIH plus the noise margin, NMH. So this should be your Vout. Here for this question, Vout is 2.75 volts and the noise margin is, in the first case, 0.1 volt. So it is 2.85 volt. So that's the Vout that you require here at this point in order to drive all the load transistors. But if you have 2.85 volts here and this point is at 5 volts, so what is the current that will flow through this collected resistor? It will be IC will be 5 minus 2.85 divided by RC, which is 1 kilo ohm. How much is that? 2.15 milliampere. So that's the current which is flowing from the supply to the output terminal and into all these load transistors. And since all these load transistors are kind of symmetric, are of equal value, you can see that RB is 10 kilo ohms, and we also assume that the B is same for all these transistors, the BE drop. So the same current will get divided and flow into each of these load transistors. So to find out the number of transistors that you can connect to it, we should find out first how much current is flowing into each of the transistors, and that you can do again by applying here. What was it? Here you had 2.85 volts and you want these transistors to be turned on. They should go to saturation. So you want this voltage drop to be 0.7 volts. Here they are given, right? VB sat and VB on are 0.7 volts. So the voltage drop across the base resistor RB is 2.85 minus 0.7. The current flowing into each of these transistors will be the voltage drop divided by the base resistance, which is 10 kilo ohms. And this is nothing but 2.15 divided by 10 milliamperes, just 0.215 milliamperes. So the total current available to you is 2.15 milliamperes, and to each of the transistor bases you have to supply 0.215 milliamperes. So how many transistors can you have? If you have n transistors and each of them needs this current IP, and in total you have only current equal to IC. So the number of transistors that you can have in the load is, that's the fan out, be IC by IB, which is 2.15 by 0.215, just 10. Next, similarly for case 2, here the noise margin is 1 volt. So your Vout should be VIH plus noise margin, which is 2.75 plus 1, which is 3.75 volts. So the current across collector resistance RC is 3.75, no, 5 minus 3.75 divided by 1 kilo ohm, which is 1.25 milliampere. And in this situation, the base current will be 3.75 minus 0.7 divided by 10k, just 0.315 milliamperes. So now the number of transistors you can connect at the output will be IC by IB equals 1.25 by 0.315, so approximately 4. It will be a little more than 4, but the number of transistors is an integer, so you can't have 4.1 or 4.2 or anything like that. So you actually have to do a floor function of this. So this will be something like 4.09 or something. The floor of that is 4. So from this question you can see that if you want to have a better noise margin, which will give you a better performance in terms of noise, then the number of transistors you can conduct to the output will be reduced. So increasing the NMH, in case 1 it was 0.1, in case 2 it is 1 volt. That decreased the fan out from 10 to 4. So the correct answer is option B. Okay. Question 5. For the given TTL circuit, find the current flowing through the 100 kilo ohm resistor when VA, input voltage at A, is 0 volts. Assume VC saturation is 0.2 volts, current amplification beta is 100 and VB on is 0.7 volts. The alpha of Q1 in its reverse active mode is 0.01. Okay, here they have given that A is low, input voltage at A is low, that is 0 volts. What that means is, since this base is connected to 5 volts through this 40k resistor, this is connected to 0 volts, this junction will be on, so all the current flows through this path, so no current will flow through this path. That means this is at low voltage and this transistor is off. Since that Q4 transistor is off, no current will flow through this 12 kilo ohm resistor and no voltage will drop across it, so there is no voltage to forward bias this VBE junction. So this, what is it, Q3 is also off. Now this Q2 is on because um, this base is connected directly to this 5 volts through this 20 kilo ohm, and there's no current flowing through this path. So there will be some current flowing through this path, there will be a small voltage drop across this 20k volts, and remaining voltage will be present at this base terminal. So Q2 will be on. Now in this situation we have to find out what is the current flowing through this 100 kilo ohms. So here there will be a collector current flowing in this direction, IC, and there will be a base current flowing here, IB. So in this path the current that is flowing is IB plus IC. So the current through the 100k ohm resistor is the sum of the base and collector currents. And the useful thing here for the transistor is that IC will be equal to beta IB, and the given beta is 100, so it is 100 times IB. Another thing is I'm assuming this diode will also drop 0.7 volts. And this drop across this VBE junction is, here you can see, 0.7 volts. Alright, now you can write the voltage equation. 5 volts, that's here, minus the voltage drop across this resistor is IB into 20k. So 5 volts minus IB into 20 kilo ohms minus voltage drop across BE junction of Q2, which is 0.7 volts, minus voltage drop across the diode, which is 0.7 volts again, minus voltage drop across 100 kilo ohms, which is IB plus IC into 100k is equal to 0. So I wrote the voltage equation along this path. And then you can use the fact that IC is 100 times IB. So you got two equations. This is 1, it is 2. You have two unknowns. IC and IB. You can solve these linear equations to find out the values of IC and IB, and it will turn out that IB is 0.35 microampere. IC is 100 times IB, so it's 35 microampere. So the current flowing through the 100 kilo ohm resistance is IC plus IB, which is 35.35 microamperes, which is option A. Any questions? Alright. Question 6. The circuit given below, what is the value of V out when both A and B are at high logic value? Consider the voltage drop across transistors, that is the VDS, to be negligible and diodes to be ideal. What will it be? I'll give you 2 minutes. This question is not very hard, so I'll give you 2-3 minutes. Try it out and type your answers in the chat box. Okay, so here both A and B are high. So since this gate voltage is high, VGS is 5 volts. So this transistor is on. Since that transistor is on and VDS is negligible, so this will also be at say 0 volts approximately. So that means since both A and B are 5 volts, VGS is sufficient here. So both these transistors will also be on. So this will be at approximately 0 volts. Again, since this is connected to the gate of B is connected to the gate of top transistor, that will also have sufficient VGS. So this transistor will also be on. So all the transistors are on. That means that this entire path gives you a path for current to flow because all the transistors are on and the resistance will be almost 0, let's say here. Ideally that should be the case. So what will happen to this circuit? It will reduce to something like this as 5 volts, a diode, 1K, another diode, 1K connected to ground, and then there's 1K here, and since all the transistors are on, there will be a path here for current to flow through. So here, since you can see that the ground is connected through the ground through this 1 kilo ohm, the P junction of this diode is connected to the ground. So this is actually always less than 5 volts. So this is actually off. And since that diode is off, we could just remove it. And this circuit would then become 5 volts, 1 kilo ohm, 1 kilo ohm, something like this. And again, this diode is also reverse biased, so this is also off. So you could once more simply write it as this as 1 kilo ohm, there's 1k, and this is just off, so there's no connection here. So this is nothing but a series of 1 kilo ohm resistors connected in, they're connected in series, so it's just a voltage divider. And since both resistors are of equal value, the voltage at this point will be half of 5 volts. So this is at 2.5 volts, and that's your Vout. So your Vout is 2.5, option D. Okay, did you get it? Any questions? You can see the last lecture from week 1 to know how MOS transistors work. So CMOS and all is covered in the last lecture. This is NMOS. That's also covered in the last lecture. Okay, on to question 7. The given VOL and VOH, also they are given VIL and VIH. You have to find the noise margins for both the low and high situations, that is NML and NMH. This is simply straightforward. Noise margin low is nothing but V input low minus V output low. This is 1.4 volts minus 0.4 volts, which is 1 volt. Noise margin high is VOH minus VIH, which is nothing but 4.5 volts minus 3.2 volts, which is 1.3 volts. So just from the first value of NML, you can see that it's option D. Just to cross check it, you can find the other value also, NMH. It's 1.3 volts. And then the second part of the question is this circuit with these values functionally better than a circuit with a different set of VIL and VIH? So we'll have to calculate the NMH and NML for that circuit also and compare. So let's call it NML dash, which is VIL dash minus VOL. So the new value of VIL is 1.5 volts minus 0.4 volts is 1.1. Similarly, NMH dash is VOH minus VH dash, which is 4.5 volts minus 3 volts. So it is 1.5 volts. So you can see that in the new circuit, the noise margins are larger. Noise margin low is 1.1, which is 0.1 volts more than the previous value, and noise margin high is 1.5, which is 0.2 volts more than the previous value. So this new circuit is actually better. So is it functionally better than a circuit with the new parameters? No, it's not better than a new one. So the higher the noise margin, the more noise we can tolerate in the circuit. So we should aim to get noise margin high. Of course, there will be other constraints that we'll have to trade off with. So this is option D. Okay, question 8. The following circuit, this is the old RTL logic circuit from Motorola. So 3 input dual NOR gate, that means there are two 3 input NOR gates here, and you can see this set of these 3 are inputs, and this is the output. So this set forms one OR gate, sorry, a NOR gate, and these 3 are also inputs, and this is the output for that corresponding circuit. So this will form another NOR gate. So there are 2 NOR gates. That's why it's called a 3 input dual NOR gate. And the question says, suppose plus 5 volts is given as input to pin number 5, 6 and 9. So this is 5, 6 and 9. They're giving plus 5 volts to all 3. What will happen? You can see that emitter is connected to ground in all of the transistors. So this 5 volts is connected to the base through this resistor R1. So all 3 transistors will be turned on and go into saturation. So when they go into saturation, the collector emitter voltage will go to VCE sat. So here in this transistor, this is collector base emitter. Emitter is at ground, so it's 0 volts. That means that this collector will be at VCE sat. And for this circuit, VCE sat is 0.1 volts. It's given here. So this pin number 10 is at 0.1 volts. Then the output pin 10 is then connected directly to pin 2, 12 and 13. So this is taken and connected to 2, 12 and 13, which are the inputs for the second NOR gate. So since 0.1 volts is a low voltage, that means all the inputs to all 3 transistors is low. That means all 3 transistors are off, and when the transistors are off, no current will flow through R2. So this entire VCC that is connected to 5 volts will appear across this second output pin, pin number 3. So the value of voltage appearing at output 3 is 5 volts. The answer is option B. Or you can just think that these 5, 6 and 9 form the inputs for the first NOR gate. Since all of them are high, output will be low. So that is given at output pin 10. That is fed to the input pins 2, 13, 12 for the second NOR gate. So all the inputs to the second NOR gates are low. Since they're all low, NOR logic will give you an output high. Output high will be 5 volts in this circuit. Okay. For the circuit given below, which of the following is or are true? Consider diodes to be ideal. So here multiple options could be correct, since they are saying which of the following is or are true. And you can see that there are only two inputs, A and B, that are being varied in the options. So there are four combinations, and they have given the output for each of the combinations. Which of these four combinations are correctly matched with the output? So when both A and B are low, there's no voltage provided anywhere in the circuit, so the output will always be low. You can't get a high output when you are not supplied any high voltage at all. So a high output would mean that you have a potential of 5 volts, right? But if you are given 0 volts to both these terminals, where will the 5 volts come from? It can't magically appear. So option D is not correct. This is not correct. Then you have B and C, where A is low, B is high, and in both the options the output is different. So one of them has to be correct among B and C. Then the third case is A is high, B is low. So we'll go through them one by one. When A is high, 5 volts is given to A. B is low, 0 volts is given to B. So this diode D1, since 5 volts is applied to the P terminal, D1 will be forward biased, and here the diodes are ideal. So for an ideal diode, if it's forward bias, it's just a wire with no resistance. If it's reverse bias, it's just an open circuit with infinite resistance. So since D1 is forward bias, it's just like a wire that is connected here, and all this 5 volts will appear at this emitter terminal. Here you have to be careful because this is not an NPN transistor. You can see the arrow given here. This is the PNP transistor. This is the emitter, this is the base, and this is the collector. So in this case, the emitter is connected to 5 volts, and then the base is connected to 0 volts. Because let's say there was any higher voltage here, if it was like 1 volts, let's say initially, that would mean that since this is 0 volts and this is 1 volts, D3 is forward biased, so it would just be like a straight line. So that would pull this voltage down to 0 volts again. So because of this diode D3, this is at 0 volts. So since this is a PNP transistor, this emitter base junction is forward biased here. So P is connected to 5 volts, N junction connected to 0 volts. So this transistor is actually on, and current will start flowing through this freely, and all that current will cause almost all the voltage to drop across this 10 kilo ohm resistor. So the output is high. So this option A is true. Any doubts in this? Did you understand how the output is high? If you didn't understand, you can ask me. I'll explain again. Okay. The next situation is A is low and B is high. So A is at 0 volts and B is at 5 volts. That means that this D3 will again be reverse biased because the N junction of this diode is connected to high voltage. So this is kind of open. And then D2, for D2 you can see that the P junction is connected to B. So this is at 5 volts. So D2 is forward biased. So this becomes like just a simple wire. So this again is connected to the emitter, you can see. So again the emitter is at 5 volts, just through a different path. And since this is at 0 volts, this will be reverse biased, and this will bring this voltage down to 0 volts. Similar to how in the previous case D3 brought this voltage to 0 volts. Here D4 will bring it to 0 volts. So again it's the same situation. There's 5 volts at the P junction, 0 volts at the N junction, so current will start flowing here. Transistor will be on, so current will start flowing through the collector, and it'll be in saturation, so high current will flow here. So this all the output, all the input that is present at B, all the 5 volts will almost all drop across the 10 kilo ohms, and a small quantity will drop across the PN junction. So output is high again. So the correct answer is option B. So both A and B are right. Yes. Hmm? Case D, when both are low. This one? Yeah, there's no other external power supply connected here, right? It's just wires and circuit elements hanging about. If both A and B are low, oh wait, yeah. If both A and B are low, this is at 0 volts, this is at 0 volts. There's no power supply anywhere in the circuit then. You're not supplying 5 volts anywhere, right? So how will this output go to 5 volts? So it can't go to 5 volts. This option D is saying that when both inputs are low, the output is high. So that's not possible, right? So option D is not correct. I just eliminated it early because it's simple. See, in any circuit, sometimes they might just not mention the power supply. They might not draw it out. But in all these transistors and all, you can see that here, see, there's a supply VCC. It's connected to a power supply that you have to give. Okay, the circuit itself won't generate that. You have to connect externally. This will be inside a chip, all these transistors and all, and this you have to connect that pin number 11 to a external power supply. Similarly in other circuits also. So there's a plus 5 volts here. The plus 5 volts is something you supply. So if nothing is supplied in the circuit, it's just a bunch of wires hanging about, and there's no potential difference. So magically there can't be a potential difference anywhere. You can't get any, yeah, everywhere it will be 0 volts. Okay. So Both these options were correct, and for this question they had asked which of the following is or are true, so they are expecting that multiple choices could be right, so both A and B. In case they allow you to only select one of the options in your assignment, then you can select any one of A and B. Okay, this is the final question. Consider the input-output characteristic of a CMOS inverter circuit shown below. Among the points A, B, C, and D in the input-output characteristics, which also mark the transition of operation state of transistors, which points can be more appropriately identified as VIH and VIL? So you can see the options. VIL, is it point A or point B? And VH, is it point C or point D? That's what you need to figure out. So think about this. I'll give you 2 minutes for this question also. Okay, I hope you thought about it. Uh, Here the answer is for VIL it's point A, and for VIH it's point D, because only below this point A will this for below point A this transistor T1 is fully off, and in this region between A to B T1 is not off. T1 will be in saturation. And again similarly above this point D, the transistor 2 T2 will be off. Here T1 will be off. So only when the T1 is completely off, transistor 1 is completely off, will you get a high output voltage, and only when the transistor 2 is completely off will you get a low output voltage. So D and A more accurately mark the cutoff point. So before this, T2 will be in saturation, and after this point T1 will be in saturation. So this point A marks the transition point when T1 goes from off state to saturation, and this point D marks the point where T2 goes from saturation to off state. So A and D can be more accurately identified as your VIH and VIL, which is option A. So this is explained kind of this all this characteristics is explained in lecture 5. So you can check out that lecture for this question. Okay, that's it for today's session. If anyone has doubts, you can ask. So first week is mostly introductory material, and this is to kind of get you to understand where digital electronics starts, but this course won't focus on these aspects that much. This is just in the first week. From next week we'll directly move on to digital electronic circuits, and it will be more towards digital electronics, the abstraction of digital electronics, let's say. And if you want, if this topic that you studied in week 1 is very interesting to you and you want to learn more, then you can try taking a course on VLSI. So in VLSI design, all these aspects will be dealt with in much more detail. Okay, I'll just stay here for till 6 o'clock. If anyone has doubts, you can type it in the chat box. Otherwise, you guys can leave. And good luck with your assignments for week 1. Yeah. Huh. Huh. Let me see. Totem pole reduces output resistance is what they're saying, right? I'm not exactly sure. Was it not explained in the lecture? So reduces output resistance in comparison to what exactly is it? Is it in comparison to a DTL circuit? Uh, I'm not exactly sure how this happens. So actually, the field I'm working in has nothing to do with digital electronics. So, but I'm teaching this course because I studied ECE long back, so I still have some knowledge. But exactly how these transistors work, I already forgotten. So one thing you can do is uh, let me see. There should be a discussion page or something, right? So in that discussion forum, you can ask this question. And there, the TAs who are directly working with the professor to maintain this course, those guys will be there, and they might actually explain it. So we are mostly responsible with problem solving sessions, so we don't go into the course materials in depth ourselves. But those guys are more directly involved, so you can ask there. All right. VLSI, what I had in my college was mostly this analog related stuff. So digital design course that will be on uh, electronics. So what for what purpose you should tell me that first? Why? What do you want to know exactly? Yeah, so yeah, you will have to look into the course contents, what exactly they're teaching. So in one of my VLSI courses, there it was purely just the analyzing the characteristics of all these transistors, uh, making circuits, analyzing CMOS logic. So it was exactly whatever stuff we covered in week one, that is extended to one whole semester with simulations and all that stuff. So they will go into a lot of depth in that. The other course that I had was digital logic design, and there they don't care about the underlying circuits at all. They only care about the abstractions. So that will deal with FPGAs and programmable arrays. So that is one type of course. You just go through the syllabus that they will have in their course info page, right? And check if there are things like FPGA and all that will be more towards logic design and not these circuits. So I could go through the courses that are being offered now and see what course it is. Let me see. So there's one course called CMOS Digital VLSI Design. So that will be all these. They'll simulate all this stuff and show you exactly how the characteristics are for all these gates and all these circuits. So that's being offered by IIT Roorkee, Professor Sudeb Das Gupta. You can just search VLSI in the SWAYAM page. So there, this type of stuff is being taught. So it will have something like that. And if it's something to do with FPGAs and all, if it's that type of work, that usually it will have something like digital logic design or logic will be there in it. I'm not sure if there's a course of being offered this in that direction. Alright, anything else? Hello. Yeah, tell me. Hello. Hello. Okay. Guys, for those who joined late, the session starts at 4 o'clock. Usually I'll be done by 5:15, 5:20. So if you come after that, then everything will be over. So you should join early. Yes. Okay. So suppose you have a gate. Okay. Some gate, I don't know what it is. And there's some input to this. There's some output. This is the input. Usually we write it as I/P. This is the output. Usually we write it as O/P. And what we want is, let's say in a digital setting, right? We have only two values if you consider binary. So your output and input, your voltage value, let's say, instead of calling it output or input, can only take two different values. Let's say you have 5 volts with you and you divide it into two parts, 2.5 volts. In digital, what we do is below 2.5 volts, everything you can say it as low, and above 2.5 volts up to 5 volts, you can say it's all high. So low, high. This is kind of what we want in a digital circuit. But the thing is, when you try to implement this practically, you won't have any circuit that will give you such kind of performance. So consider a NOT gate, okay? You have a NOT gate. What should a NOT gate do? If your input is below a certain point, right? This is your input Vi, this is your output Vo. If your input is low, and let's say this is low, this is what I consider as low, then your output should be high. So you should get a high value. And if your input crosses this threshold, let's say this is 2.5 volts, your input goes above 2.5 volts, you will consider it as high, and you want an output that is low. So it should be something like this. So this is kind of the input output relationship that you want in your circuit. Okay, did you understand this part? Okay, so you kind of have one threshold, 2.5 volts. Below that, you consider it as input low, and you would want a high output. Above that, you consider it as input high, and you want a low output. This is what you want ideally, but what happens is you can't get a circuit like this in real life. So always in real life, whatever you try to do, you will get something that is like this. Okay, there won't be a sharp transition here. So the let's say this is your 2.5 volts midpoint, this is 2.6 volts, and this is 2.4 volts. So right at 2.4 volts itself, your output will start going lower and lower. So in this portion, there's kind of an ambiguity, right? You don't know whether the circuit can't tell whether it's a low or high. Again, this portion you have an ambiguity. So what we do is we'll say ignore this entire portion. Okay, I will make sure that my circuit does not consider all these voltage values. So at this point, what do you have if you ignore all this? You have something like this. So all these input values between 0 to 2.4, you consider it as a low value, and all these input values between this is 2.6 and whatever up to 5 volts, you will consider it as high. So this is what you work with in real life, and you try to ignore the parts in between. Suppose some circuit actually goes to this input value. Suppose someone deliberately gives 2.5 volts, then the circuit that you design might not work as intended, but it's okay. You are saying that I won't give 2.5 value volts ever. Okay, this will give rise to a concept of VIL and VIH. So from the input side, you say this is VIL, and if your input voltage is less than this, you will consider this as a low voltage. And VIH, if your input is more than this, you will consider it as high, and you will ignore this middle portion. That's what you are doing. So there are two different values here for any gate, for a NOT gate. there will be an input voltage and an output voltage, and the high and low values for your output might not be the same and as the high and low values for your input. Okay, so for the output stage, it depends on what precision you want, right? Depends on what type of circuit you want. Most of the time you don't want the same, you don't really need the same input and output high and low values, so that will give rise to a difference. So if you connect two of the same circuit elements in series like this, okay, the output of, let's say, uh, this is not gate 1, this is not gate 2. The output of this not gate 1 is the input of this not gate 2, right here. Okay, okay, just for clarity, let's give some values. Let's say for this not gate, the output high value is 3 volts. Okay, let's say for the same not gate, for the input side, the high value is 4 volts. Let's consider this. Let's say you give some low value here, some input low. What will the first not gate do? The first not gate should give you a high output, right? So according to the not gate, what is a high output? It's anything above 3 volts. So let's say it gives you only 3.5 volts, right? So according to the perspective of this first not gate N1, it gave you a high output. So it's happy, it doesn't care. Now you look at it from the perspective of the second not gate. It is seeing 3.5 volts at the input. But the second not gate, its VIH is 4 volts. That means it needs at least 4 volts to consider the input as high. But you are only giving it 3.5 volts. So the second not gate won't be able to tell that this is actually high voltage. It will say this voltage is not high. And this might not operate however you want it. So if you give two NOT gates in series, if you give low here, you should get a high here, and that high is input to the second NOT gate, so the second NOT gate should give you out a low. But here in this situation, that might not happen, right? Did you understand what I am saying? So this VOH and VIH must be kind of matching. The high input value should be smaller than the high output value, so that, let's say, this VIH was not 4 volts but it was also only 3 volts. In that situation, what will happen? The first NOT gate gave out 3.5 volts, which is actually more than VIH for the second NOT gate, right? So the second NOT gate will also think, okay, this guy has actually sent me a high voltage. My input is actually a high voltage. So it will give out a low output now. So that's why the VOH, VH and all are important. And now when it comes to noise margin, again you consider the same scenario where you connected two of these elements in series. Let's consider a low situation. Let's say for this NOT gate, for the output, the low value is considered to be zero point 0.2 volts. Okay, so whenever you give a high input, whatever it is, this NOT gate will give you something 0.2 volts or below in this region. But for the second NOT gate, anything below, let's say 1 volt, which is Vi, let's call this Vi low, VI low. 1 volt, it will consider as a low value. Okay, so according to the second guy, anything below 1 volt is low. But whenever the first guy wants to give a low output, it will only give you something below 0.2 volts. So in this situation, what happens is, if there's some mistake in the middle, if someone is interfering in the middle, okay, here someone is actually adding, let's say, zero point 0.5 volts, someone adds it just to cause trouble. So then what will happen? The first guy will give you something less than 0.2 volts. The middleman will add zero point 0.5 volts to that in the hopes that he will mess up the working of the circuit. So what the second guy sees is 0.7 volts now, right? That is the input to the second guy. But since VIL is 1 volt, this is still somewhere here. This is still below 1 volt. So the second transistor, second gate still thinks that it is a low volt. So there's no real problem that is caused by adding zero point 0.5 volts here. So this gives you kind of a margin of error, where instead of giving zero point 0.2 volts as the output, if some noise gets added to this, so some random noise, as long as it is that noise is between this difference level, it is still considered as low by the second gate. So this is your noise margin low. Did you get it? Hmm? Okay. Similarly for noise margin high also, it's not much different. So at this output of the first gate, let's say anything above 4 volts is high. That's what the first guy thinks. So he gives you 4 volts, and some middleman, some channel will add noise to it and make it go to 3.5 volts, let's say. So this can't be controlled by the first inverter. It gave you 5 volts. According to it, the job is done. But you're actually getting 3.5 volts at the input of the second inverter. But luckily, this second inverter, let's say it considers anything above 3 volts as high. So even though this 4 volts got reduced to 3.5 volts by noise, second inverter still considers this signal as high. So there's kind of a margin, a room for error that you have in the high side also. So this room for error is called the noise margin at the high side, noise margin high, NMH. Okay. And other thing you wanted to ask was transition width, right? Transition width is not complicated. Here, at the input side, you have some logic value VAL, below which everything is considered as a low value. There's some value VIH, above which everything is considered as high value. So suppose you want to change your input that you're giving to a circuit from high to low. Initially, let's say you had a NOT gate. Input you are giving high input, and then something else happened in the circuit and you want to give a low input now. So you want to change this high input to a low input. So what is the minimum amount of voltage difference that you need to change your input by to get a transition? This is a transition, right? From high to low or from low to high. That's a transition in the state of the input. So to get this transition, what is the minimum amount of voltage difference you need to apply? That is called the transition width. So let's say you are at the very edge here. Suppose this is 4 volts and this is 1 volt. So you are giving a high input which is at the very edge 4 volts. Now you want to change your input to voltage low. What do? You can come to the very top and start giving it 1 volts. So you reduced your voltage from 4 volts to 3 volt to 1 volt, which is a reduction of 3 volts to change the state from high to low. Or suppose you started off at 1 volts, which is a low voltage, and then you wanted to change your input to high. So what you can do is change this 1 volt, keep changing it until you reach 4 volts, at which point the circuit will consider it as high voltage. So the change in your input voltage was 4 volts minus 1 volt again, this 3 volts, an increase of 3 volts to change from a low state to a high state. So the difference in VIH and VIL is called the transition width, because that is the minimum amount of voltage change required to transition from low to high or high to low. Okay. All right. Okay, that's it for today. Unless you have any other doubts, I'll leave. From next week, we'll start with digital electronics properly. This is just an introduction. Okay, guys, thank you for attending. Bye.